We would be discussing about binary multipliers. Just like in the decimal system, we also have multiplication on the binary system, and the procedure is also same. Let's consider an example for this. We have a two-bit binary bits B0 B1 and A0 A1, and we start multiplication from the rightmost bit. We do multiplication of A0 B0 and we write it here. A0 B1 we write it here. Okay, just like in the decimal system. And we also do the multiplication of A1 B0, we write it here, and A1 B1 we write it here, and we do the additions afterwards. Okay, now the C0 is exactly same as that of A0 B1. Okay, that comes down directly because 0 is there on the bottom, and the addition of these two bits would be given to C1. If there is any carry, it would be transported back to next bit calculation, and the result would be C2. And if there is again another carry, that would be transported to the next bit, and that comes directly as C3. Okay, we can summarize the result as here, as C0 would be A0 B0, C1 would be the addition of these two bits, C2 would be the addition of this and the carry of this, and C3 would be directly the carry of this. Okay, there is no extra bit of additions there. So if you're going to implement that onto this combinational logic, you see C0 would be exactly that of A0 B0. C1 would be, as we are doing a 2-bit addition, we can take on as A0 B1 and here as A1 B0. So we can use half adder for this operation, and the carry out of this would be given to this one, the next bit calculation, and we can get the C2 as the solution and C3 as the carry, which will give us a 4-bit solution here. Now this one is for a 2 by 2 bit multiplication. Now we have a generalized rule here, which you can look for the book, and we will find this rule given there. Suppose we have a j multiplier bit and k multiplicand bit. We need j by k, that is j times of k, and gates j minus 1 k bit adder to produce a result of j plus of k bit. Suppose we have a multiplier bit of 3 bits, that is a0, a1, a2, and a multiplicand bit of 4 bits, that is b0, b1, b2, and b3. So according to the rule, it says us that we need 12 AND gates, 2 4-bit adders to produce a result of 7 bits here. Okay, so if you follow the very first procedures as I have discussed earlier, you will get this as the matrix. I've already told you C0 comes down directly as of A0 B0, that comes always. We do the next bit addition, we get C1. We do the next bit addition, we get C2, C3, C4, C5, and C6. C6 remains 1 or 0 depending on the carry out. Okay, to implement that, we need 12 AND gates, 2 2-bit 4-bit adders to produce a result of 7 bits. So this would be your combinational circuit to implement that. Okay, this one would be your first bit, this one would be your second bit. Okay, and the final result would be a 7-bit result. Okay, so as I have already told you, we need two 4-bit adders. This one would be your first 4-bit adder, this one would be your second 4-bit adder. Okay, now C0 is exactly that of A0 B0. Okay, what about the next? What we do is here we take on as we consider this 0, and we do the first 4-bit adder to add these 4 bits. Okay, you see the first one is 0, which is represented as here, this 0, whereas the rest of the 3 bits are given here, and the next 4 bit are given here. So we use the first 4-bit adder to do the addition of these two numbers. Whatever we get with a carry, you see, this is what we get, the answer. Okay, The final bit, this bit goes down to C1. Okay, C1 goes to directly like C1, and we have also taken that here. This is the C1 bit that is directly given as input, directly given as output C1, and this one would be your carry and rest of the 3 bits here. Okay, these are the 3 bits along with the carry. Okay, so what we do is we use another 4-bit adder to add these 4 bits. So that goes to your second 4-bit adder. Okay, these are the 3-bit solutions we get. We get the extra carry, that is C, and we use this second 4-bit adder to implement the very same thing. Okay, and that's in this particular way we use 2 4-bit adders, and the answer would be the 4 bits along with a carry, and that will create us a total 7-bit result. Okay, so that's the step-by-step addition here. You can look for the book and you will find the detailed picture there. Okay, it's the exact same book, exact same figure for the book, and you can look for the procedure with which the solution is calculated, and you can implement by using this particular rule. You can implement any type of any j by k bit multiplier. You can implement or design any j by k bit multiplier with required instruments like AND gate, 4-bit adders, or n-bit adders to produce a result of j plus of k bit. Okay.